Guys, Hi guys, my name is Vaishnavi. I am studying in Sri Venkateshwara College of Engineering. The subject is data structure. The topic is optimal binary research tree. Introduction. An optimal binary search tree is a binary search tree that minimizes the average research time for a given set of keys. It is an efficient data structure that allows for first researching, insertion, and deletion operation. This concept of optimal binary search tree was first introduced by Donaldo Kunt in 1971. Basic of binary search trees. A binary search tree is a binary tree where each node has a key and satisfies the property that the key in any node is greater than the keys in all nodes in its left subtree and smaller than the keys in all nodes in its right subtree. Binary search tree enable efficient researching, insertion and deletion operation with an average time complexity of O log n, where n is the number of elements in the tree. However, the efficiency of a binary search tree depends on the order of the keys. Importance of optimal binary search tree. In a binary search tree, the average search time depends on the distribution of the keys. An optimal binary search tree ensures that the keys with high frequencies are placed closer to the root, reducing average research time. By minimizing the average search time, optimal binary search tree improve the overall efficiency of search operation. Constructing the optimal binary search tree. The optimal binary search tree is constructed using the root table. Starting from the root of the entire tree, the left and right subtree are recursively constructed. The process contains until all keys have been placed in the tree. Access frequencies. The access frequencies of each key or element are determined based on historical data or assumption. Higher access frequencies result in lower search cost as the keys are accessed more frequently. The access frequencies can be adjusted dynamically to accommodate changes in usage patterns. Dynamic programming. Dynamic programming is used to solve the optimal binary search tree problem efficiently. The problem is broken down into smaller subproblems and the solution are stored in a table. The optimal binary search tree is constructed by combining the solution of the subproblems. Dynamic programming approach. The dynamic programming approach is used to construct optimal binary search tree. It involves solving subproblem or building up the solution from smaller subproblem. The optimal substructure property is crucial in this approach all as it allows us to solve larger problem by combining solution to smaller subproblems. Dynamic programming algorithm. The dynamic programming algorithm for constructing an optimal binary search tree involves two steps: calculating the cost and root tables, constructing the optimal binary search tree using the root table. Optimal substructure property. The optimal substructure property states that an optimal solution to a problem contains optimal solution to its subproblem. In the context of optimal binary search tree, the optimal substructure property implies that an optimal binary search tree for a given set of keys can be formed by combining optimal binary search tree for its subsets. Optimal binary search tree problem. The optimal binary search tree involves finding the minimum cost of searching in a binary search tree that can be formed from a given set of keys where their respective frequencies. The cost of searching is typically defined as the sum of the frequencies of the keys accessed during the search operation. Optimal binary search tree algorithm. The algorithm for constructing an optimal binary search tree consists of several steps. Constructing a cost matrix to store the cost of searching for different key combination. Calculating the optimal cost matrix using dynamic programming. Backtracking to construct the optimal binary search tree based on the optimal cost matrix. Cost function. The cost of searching in an optimal binary search tree is calculated using a cost function. The cost function takes into account the access frequencies and the depth of each key in the tree. The goal is to minimize the total cost, which is the sum of the cost of all search operations. Constructing the cost matrix. The cost matrix is a square matrix that stores the cost of searching for different key combinations. The diagonal of the cost matrix represents the cost of search for individual keys. The upper diagonal represents the cost of searching for key combination. Calculating the optimal cost matrix. The optimal cost matrix is calculated using the dynamic programming approach. The algorithm iteratively fills the cost matrix considering different lengths of subsequence of the keys. The optimal cost for a subsequence of the keys is determined by considering all possible routes and their corresponding costs. Filling the cost matrix. The algorithm fills the cost matrix in a bottom-up manner, starting from subsequence of length 1 and gradually increasing the length. At each step, it considers all possible routes for the subsequence and calculates the corresponding cost. The minimum cost among all possible routes is stored in the cost matrix. Backtracking the construct the optimal tree. After calculating the optimal cost matrix, we can backtrack to construct the optimal binary search tree. Starting from the root, we can choose the key with the minimum cost as the root of the tree. We recursively construct the left and right subtrees using the keys on the left and right side of the chosen root respectively. Example. Let us consider an example where we have keys A, B, C, D and E with access frequencies 10, 5, 20, 15 and 12 respectively. We can use dynamic programming to construct the optimal binary search tree for these keys. The resulting trees will have the structure that minimizes the total search cost. Cost table. The cost table stores the cost of searching for each key at each possible subtree. It is filled in a bottom-up manner starting from the smallest subtrees. The cost of searching for a key is the sum of its access frequency and the cost of its left and right subtree. Root table. The root table stores the optimal route for each subtree. It helps in determining the structure of the optimal binary search tree. The root of a subtree is the key that minimizes the total cost of searching in that subtree. Example of cost and root table. The cost table for the example will show the cost of searching for each key at each possible subtree. The route table will show the optimal route for each subtree. Complexity analysis. The time complexity of constructing an optimal binary search tree using dynamic programming is O. Bracket n to the power of 3, close the bracket, comma, where n is the number of keys. This is because the algorithm involves filling a cost matrix for size n into n and requires 3 nested loops. The space complexity is O. Bracket n to the power of 2, bracket close, since we need to store the cost matrix. Optimizing space complexity. The space complexity of the optimal binary search tree algorithm can be optimized to O of n using the concept of rolling arrays. By only keeping track of the current row and the previous row of the cost matrix, we can reuse the space and reduce the space complexity. Optimizing time complexity. The time complexity of constructing an optimal binary search tree using dynamic programming is O, n to the power of 3. This is because the algorithm fills in the cost and route tables for all possible subtrees. However, the table can be computed efficiently using memorization to avoid redundant calculations. Variations. There are variations of the optimal binary search tree problem, such as the static optimal binary search tree. The static optimal binary search tree assumes fixed access frequencies and is solved using similar techniques. Other variations consider different cost function or additional constants. Application of optimal binary search trees. Optimal binary search trees have various applications in fields such as information retrieval, language modeling, and compiler optimization. They are used to improve the efficiency of search operation in large data sets. Optimal binary search trees are also used in code optimization to minimize the time complexity of searching for variables and functions. Limitations of optimal binary search tree. The construction of optimal binary search trees using dynamic programming can be computationally expensive for large data sets. The algorithm assumes that the frequencies of the keys are known in advance, which may not always be the case. Optimal binary search trees may not be optimal in practice if the distribution of the keys changes. Advantages of optimal binary search tree. Optimal binary search tree provides faster search preparation compared to non-optimal binary search tree. They reduce the average search time by placing frequently accessed keys closer to the root. Optimal binary search tree improves the overall efficiency of search operation in large dataset. Conclusion. An optimal binary search tree is a binary search tree that minimizes the average research time for a given set of keys. The dynamic programming approach is used to construct optimal binary search tree by solving smaller subproblems and combining their solution. Optimal binary search tree provide faster research operation and improve the efficiency of search operations in large data sets. Thank you.